In this video, we're going to take the combined gas law, deconstruct it a little bit, and then take the deconstructions and relate them to the kinetic molecular theory. Now, we started with the ideal gas law, which is PV equals nRT. Then we took that and derived the combined gas law, which is P1V1 over N1T1 equals P2V2 over N2T2. From the combined gas laws, we can now actually derive 4 gas laws named for other people, and those are Boyle's law, Gay-Lussac's law, Charles's law, and Avogadro's law. For Boyle's law, we'll keep N and T constant. For Gay-Lussac, we'll keep volume and moles constant. For Charles, it's pressure and moles. And for Avogadro's, we keep volume and temperature constant. And the nice thing is you don't need to memorize the eponyms, but if you understand the conditions, you can derive all of them from the combined gas law. Now, the kinetic molecular theory deals with movement and the average kinetic energy, or other words, speed, of gases. Remember the 5 assumptions. Gas molecules have no volume, and there's no intermolecular forces between the gas molecules. The gas molecules move rapidly and in straight lines until they collide with something. Those collisions are totally elastic, and the average kinetic energy of a gas, and thus its speed, is directly related to the temperature in the Kelvin scale. And for this video, and for thinking about gases, the third assumption, that the gas molecules move rapidly in straight lines, is really important, because pressure is collisions with the container wall per unit time. I use collisions per second. We will be relating everything back to that. So let's start with Boyle's law. Here we're going to keep the number of moles and the temperature constant. So you start with the combined gas law. Since N1 equals N2 and T1 equals T2, they cancel out. And so you get Boyle's law, which is P1V1 equals P2V2. From the kinetic molecular theory, you start with a container with gas molecules. We're not going to change the temperature, so we're not going to change the speed. We're not going to change the number of moles. We change the volume. In this case, we compress it. When we do that with a decrease in the volume, the distance a gas particle has to travel decreases. Therefore, at the same speed, there'll be more collisions per second, so the pressure goes up. Vice versa, if I were to increase the volume, the distance would increase, so the collisions per second would decrease. Therefore, we can state that under constant moles and constant temperature, pressure and volume are inversely related. If one goes up, the other must go down. Here's an example. Put some xenon into a expandable container, a balloon or a piston. At 25 degrees Celsius, the volume is 2.5 liters, and the pressure is 735 torr. You keep the temperature the same, you don't add any more gas, but we decrease the volume to 1.75 liters. What's the new pressure? Stop, figure it out, come back, we'll go through it. And the correct answer is 1,050 torr. As we said, T and N stay constant, so the equation becomes P1V1 equals P2V2. P1 is 735 torr, V1 is 2.50 liters, P2 is unknown, so we keep it P2, V2 is 1.75 liters. Plug the values in, rearrange to solve for P2, and when you do that, you get 1,050 torr. On to Gay-Lussac's law. Here, we want to keep volume and moles constant. So starting with the combined gas equation, we remove the things that are remaining constant, and you'll end up with P1 over T1 equals P2 over T2. From a kinetic standpoint, you start with a container. The gas particles have a certain average speed. If you increase the temperature is a marker of the speed of molecules. So if you increase the speed but keep the distance the same, you're going to have more collisions per second, so the pressure will go up, and vice versa. If you cool things down, you slow down the particles, there are fewer collisions per second for the same distance. This means pressure and temperature are directly related. When doing these calculations, the pressure must be in Kelvin. So here's an example of Gay-Lussac's law. You have some sulfur hexafluoride, and it's at 1.50 atmospheres. The temperature is 27 degrees Celsius. You then raise the temperature to 177 degrees Celsius. What's the new pressure in the container? Once again, stop, go through it, come back, check, and then we'll walk through it. Go. And the correct answer is 2.25 atmospheres. We're keeping volume and moles constant, so the equation becomes P1 over T1 equals P2 over T2. P1 is 1.5 atmospheres. We don't know what P2 is. T1 is 27 degrees Celsius, which you have to convert to Kelvin. That's 300 Kelvin. T2 converts to 450 Kelvin. Plug the values in, rearrange to solve for P2, and you get 2.25 atmospheres. So now on to the third derived law. That's Charles' law. Here we're holding the pressure and the number of moles constant. Start with the usual equation, remove that which stays constant, and you get V1 over T1 equals V2 over T2. You start with a container at a certain volume. The molecules are at a specific speed. There are X number of collisions per second. Because the pressure is to remain constant, the number of collisions per second has to remain the same. If you then speed up the gas molecules, the volume will have to increase, because if you don't increase the volume, then the number of collisions per second will go up. That would increase the pressure, but the pressure is constant. So by increasing the volume, you increase the distance the molecules have to travel, and the volume will continue to increase until the collisions per second is the same under the second set of circumstances than the first set of circumstances. And of course, this is true in the other direction. So volume and temperature are directly related when you hold pressure and moles constant. And once again, the temperature must be in Kelvin. So let's do one quick example of a Charles' law calculation. You've got a balloon at 8 liters with 2.75 moles of helium, and it's at 25 degrees Celsius. The balloon is then tied off, so the number of moles of helium cannot be changed. The balloon is then placed into a freezer. You go back the next day. The volume is 6 liters. What's the temperature of the freezer in Celsius? You know the drill. Get the answer. Come back. We'll go through it. And the answer is negative 49.5 degrees Celsius. We're keeping pressure and moles constant. So the equation must be V1 over T1 equals V2 over T2. Our V1 is 8 liters. Our T1 is converted to 298 Kelvin. Our V2 is 6 liters. And our T2 is the unknown. Plug the values into the equation. Rearrange the equation so you can solve for T2. When you do that, you get 223.5 Kelvin, but the question asks for the answer in Celsius. So you have to subtract 273, and that gives you the negative 49.5 degrees Celsius. And last but not least is Avogadro's law. Here we're holding volume and temperature constant. So the combined gas equation, when you remove that which is constant, becomes this equation, P1 over N1 equals P2 over N2. From the kinetic molecular viewpoint, you start with a container of a certain volume. The molecules have a certain speed. We're not going to change any of those, but we are going to increase the number of particles. The more particles at the same speed and the same distance will still increase the number of collisions per second. That increases the pressure. So pressure and moles are directly related when volume and temperature are constant. So here's our last example. You've got 16 grams of oxygen placed in a rigid container at 298 K. Under this set of conditions, the pressure is 2.40 atmospheres. A little while later, you add another 8 grams of oxygen. You don't change the temperature, and it is a rigid container. What's the new pressure? Stop, get the answer, then we'll go through it. And the correct answer is 3.60 atmospheres. We're keeping the volume and the temperature constant. So we start with Avogadro's law. P1 is 2.40 atmospheres. N1 is 16 grams divided by 32 grams per mole. So you have half a mole of oxygen. We don't know what pressure 2 is. Now we added another 8 grams of oxygen. 16 plus 8 is 24. 24 grams divided by 32 grams per mole is 0.75 moles. We plug the values into the equation, rearrange the equation to get P2, which is 3.60 atmospheres. So to review, you've got 4 eponymous gas laws that can be derived from the combined gas law. You have Boyle's law, Gay-Lussac's law, Charles' law, and Avogadro's law. All 4 laws can be explained by KMT, and it all comes down to collisions with the container wall per unit time. For Boyle's law, you'll hold temperature and the number of moles constant, so you get P1 V1 equals P2 V2. From the kinetic viewpoint, what you're doing here is keeping the number of things and the speed constant, but you're changing the distance that has to be traveled. If you decrease the distance, collisions go up. If you increase the distance, collisions go down. Thus, pressure and volume are inversely related. For Gay-Lussac's law, you're holding volume and moles constant. You end up with P1 over T1 equals P2 over T2. If you maintain the same distance to be traveled, the volume, and the same number of molecules, the number of moles, then if you change the speed at which the particles travel, you have to change the number of collisions per unit time. If one goes up, the other goes up. If one goes down, the other goes down. So P and T are directly related. Charles's law. Now you're holding pressure and moles constant. This is the equation you get. If you're keeping the number of particles the same and you want to keep the number of collisions per unit time the same, then as you alter the speed, you must alter the volume and you must alter them in the same direction. That means V and T are directly related. They will change in the same direction. Avogadro's law. Here, volume and temperature are held constant. You end up with P1 over N1 equals P2 over N2. So if you keep both the speed and the distance to be traveled constant, but you change the number of particles, then the collision of particles with the container wall per unit time must change. They must change in the same direction. More particles, more collisions, fewer particles, fewer collisions. So P and N are directly related. You don't have to memorize the eponyms. You don't even need to memorize the laws, as you can derive them from the combined gas laws, which is on your equation sheet for the exam. And if you have trouble thinking about the KMT, go back to my bumper car analogy. In the next video, there are two other eponymic laws, but we won't use the kinetic molecular theory with them per se, but they do make sense.